Hi, Enoch. Thank you for joining. Hey, everyone. Thanks for joining. I believe some of the links that for this meeting wasn't sort of disseminated properly. So if you guys can help us by forwarding the Teams link to your contacts, the ones that would be interested to join, yes, please help us by doing that. But I believe those ones that are joining have joined through the IEPNG, the POM branch WhatsApp group chat. So we'll just give a couple more minutes for a few more to join.
Yep.
Hi, Puri, welcome.
Great.
All right. My phone says 12 o'clock and my laptop saying 11:59. So we'll just make a start. Yeah, good day, everybody. Thank you for joining. Our first technical talk for the year. Um, I guess we've had a couple before this, but as I think for the new leadership, this is the first one that we're hosting for the year. So thank you all for joining. My name is Mefi Boshet Esop. I am a mechanical engineer with Kramer Asia Pacific, and I will be your host and facilitator for today on behalf of the IEPNG POM branch. So this initiative for the technical talks is basically supports why the IEPNG body exists and why we do what we're doing, and is to foster collaboration, capacity building. Sorry, there's a bit of people joining right now. Let me just admit them. Yeah, as I was saying, to foster collaboration, capacity building, and just continue to support that professional development within the engineering space, whether which industry you belong to. So we try to make it fair for everybody that's a recipient or going to be participating in this sort of technical events to share knowledge all around. So I won't take too long. That's a little bit about IEPNG and what we're doing. I hope you guys enjoy this presentation. I'll hand it over to Jesse to take over and run us through this next hour through his presentation. So thank you, Jesse.
Hi, everyone. I'll just share my screen. Just give me a second. So before we start, just a little bit on housekeeping, sort of, probably a couple. If you do have questions, just put it in the message or the chat, and then later down at the end of the presentation, we'll try and answer those questions at the end. I think Murphy will record this presentation as well. And so I think in terms of obtaining a copy of this presentation, you can probably reach out to Murphy if you do wish to.
Yes, on that note, I will drop my email. If you guys do want to reach out, I might upload the recordings onto a Google Drive and you guys can access that. Yes, so thank you, Jesse.
Okay, so just thanks everyone for joining in to this presentation on de-risking your mill. Basically, there's most of the things that we'll cover in this presentation are well-known practices in the industry. And in the first part of the presentation, we'll sort of run through all those aspects very quickly. And then towards the end, so we'll try and give more time towards the end with some, I guess, key examples, which hopefully from this presentation, that's something you can take away from. Can you all see my screen? Yeah? Can you all see my screen?
Yep.
Okay.
Yep, that's it.
Okay. So this is the agenda, I guess, for today. So we'll get into the introductions in a second. So basically, we'll touch on a few key aspects, including maintenance strategy, inventory management, and then sustainable mill operations. And then we'll try and sort of quickly go over those, and then hopefully leave some more time at the end for catastrophic failure modes. And we'll try and put some examples in there and go through those examples of what we've experienced. Again, this is, as I said, most of the parts in the first part will be pretty much very common. And for those that are relatively green in the industry, I do have a couple of slides at the beginning just to sort of explain what we're sort of talking about here. Okay, so introductions. So I will be your presenter for today, as Murphy has mentioned. So my name is Jesse Garrow. I am part of the Grinding Mills Digital Inspections team here at Metso. I am a mechanical engineer, finished from Unitech. So again, began my career in Octedi through the graduate development program. And then I commenced with Metso in 2024, sorry. So yeah, that's a little bit about myself. Okay, so this part here is just essentially to sort of give an idea of, for those who don't necessarily are involved in the industry of grinding or even mineral processing plants. This is a typical sort of flow chart of a process plant for a copper processing plant. So circle here is where sort of what we're talking about. Again, grinding mills, they can be horizontal or vertical grinding mills. Essentially, the ore that comes from the mine or the run of mine goes through a crushing process. It's basically a whole process is to break down, I guess, rocks and dirt so that those valuable minerals can be exposed towards the end. And that's what obviously is the value. Grinding mills, as you can see, is that's where it comes into the process plant. It's the grinding. Basically, you have grinding media in there, and then obviously the ore and slurry. A lot of power that's required to sort of separate those rocks and dirt from the minerals itself. So that's sort of where it fits in the whole process plan. Obviously, you got the downstream processes, which classification, flotation, to just basically more separations to eventually get that concentrate or the final product, whether it be gold or copper. But in this example, it's a copper processing plant. So again, this is a horizontal grinding mill. Again, this slide is intended for those who are new and don't know anything about grinding mills. This is a horizontal grinding mill. As I said, there's vertical grinding mills. That's just a different product. So with Metso, we sort of one of the, I guess you could say, equipment manufacturers, and this is one of the specialties apart from other offerings that Metso offers. I specifically talk about grinding mills because that's been my, on large part, my experience with grinding mills. Essentially, all comes from the mine, goes through the whole processing plant via conveyors, and then this, I guess, goes to a SAG mill and then passes through down to a ball mill. Ball mills generally go through the process of breaking down those ore materials so that, as I said, exposing those valuable minerals. So why do we have to, I guess, de-risk a mill? Why is it important to de-risk your mill? So the couple of pictures to share here, just to show the importance of, I guess, why we have to de-risk your mill in the first place. It's like a sort of an intro montage of just failures. So we can see here that's a trunnion head interface. That's one of the key, because of the geometry, it's a high stress area. So if you have I guess, wash or erosion in that area, it's very prone to cracking and even fracture in extreme cases. So this is just an example. This one's a rather unhappy inch drive. So it's a fractured shaft on the pinion, a damaged gearbox. So again, very common issues. If you're not especially with Metso, unfortunately, we get to sort of see this a lot more common because of, I guess, the business. It's more involved in grinding circuits, and so customers tend to come to Metso for solutions, and this is what we sort of see every day. But for some of you, this is probably sort of new, but that's okay. We'll try and answer those questions if you do have them. To say cracked bearing pad. So again, lack of lubrication seems to be the failure sort of mechanism there. Then fractured gear tooth on a girth gear. So collapsed mill. So yep, essentially this next slide, there's a lot to sort of go through, but like I said, I will sort of try and go through quickly the first part, which is key aspects of sort of de-risking your mill. And then we'll try and leave some more time at the end for catastrophic failure mode. So again, basically de-risking your mill is just good maintenance practice and just knowing your operation limits and I guess staying within those operation limits. I won't sort of take a deep dive too much on maintenance strategies or things like that, but it's just key aspects to be covered in this presentation. So the first one, maintenance strategy. Again, different sites have sort of different ways to track and develop maintenance strategies. There's there's methodologies that are in place in which you can sort of employ to methodically identify different failure modes or how a machine could fail. And those maintenance tactics that you sort of employ at the end are sort of directed towards hopefully addressing those failure modes, or at least most of the failure modes that you can identify from those. You could use, tools like FMICA or RCM studies to sort of systematically sort of approach different ways in which an equipment could fail, and try to direct maintenance strategies towards addressing those failure modes. And so this is sort of an example of just a snippet of what a maintenance tactic could look like. Again, it's different. The systems that I guess companies sort of employ to track and monitor different failure modes and frequencies in which they occur. And there's a way to sort of track which failure modes are, I guess, more frequent in different machines, and try to optimize those so that if the work procedure is not sufficient enough to cover or sufficiently address those failure modes, then that's how you sort of close the loop in terms of optimizing it continuously. And again, to the last point there, it's quite easy to poorly do this maintenance strategies if you don't have, I guess, a well-experienced team to do it. This is one of the common maintenance strategies that's used throughout the industry. Again, like I said, it's most of the things is going to be probably common knowledge and something that's very commonly practiced throughout the mines. So one of them being condition-based maintenance strategy. So again, with mills, you got your pinion bearings, the motor bearings. A good example is vibration analysis as a method of sort of monitoring and tracking and ensuring these components are working within acceptable sort of vibration levels. And it's always good, companies sort of have a way to manage those, and they have database in which they can set trigger points for that sort of triggers them to attend to or further inspect if there's problems. So again, that requires regular inspections to measure the condition of different components in the drivetrain. It does help to understand, I guess, what the drivetrain components, the functions are, and how they fail or what would cause them to fail. Time-based tactics is another sort of common strategy that's employed. Again, condition-based tactics are consistent. If they're consistent, then time-based tactics sort of are employed. So an example there is mill liner replacement. So again, we'll sort of later touch on about knowing your limits. So mill liner replacements can be time-based, and most of the time it's time-based, on the condition that you sort of stay most of the time within the limits of your operating capacity or the way in which the mills are designed to do. So again, that might include charging levels, the type of ore body that's coming through the mill, things like that. So as long as those parameters are kept consistent within, then you more than likely would have a predictable time in which those liners will sort of wear out and they're ready to be changed out. So it can become a time-based strategy. And then you could obviously, sort of optimize that as you go, so if you go to an inspection and then there's more meat in the liner, then you could probably, sort of reduce, increase the inspection frequency or reduce the frequency, so I must say. And then you got components whose conditions are not easily inspected. often managed by time-based. So again, heat exchanges is an example. So we'll sort of cover it at the end. There's parts or interfaces in the mill joint where it's hard to inspect. So your best bet is to rely on time-based tactics to inspect those sections of the mill, and it gives you enough at least time to sort of plan properly. And then the last point, there's components with a shorter life, often simplified to time-based. So feed spouts or retainers. These are, again, during operation, you can sort of visually inspect them, but they generally are high-wear components. And then the last strategy is the run-to-failure strategy. It's only dependent on the wear profile the failure profile of the component you're dealing with, and I guess the consequence. So if that equipment or component fails, if there's what are the consequences in terms of production or even safety. And I think the more key point here is that if you choose to run with that strategy, then do you have spares, or at least you have to have spares at sufficient level to ensure that there's no the consequences of running out of spares does not directly impact too much on the production or even safety. So I put some examples in there. So instrumentation, electronic components, hydraulic valving, things like that. So again, when considering these run-to-failure tactics, it has its place, I guess, in maintenance strategy, but there's things that you have to consider. As I mentioned, is there redundancy, or how quickly, in terms of maintainability, how quickly can it be replaced or repaired, and spares being one of the important aspects into consideration here. Okay, so the common issues that we sort of see when it comes to maintenance strategies. So we got missing tactics for failure modes. So again, the examples here, you got mill shell wash erosion. So most of the things that we see sites tend to miss are having maintenance strategies or maintenance PMs in place to inspect those components. So wash, it's something that does not necessarily it's for different sites, it might not be a common issue, but if you don't have sort of a maintenance PM in place to, during reline, for example, go in and just have a look at the rubber backing inside the mill itself. Again, the mill has rubber backing that's meant to sort of put a seat on liners and provide that cover for joints behind the liners. And so if that's not properly inspected during those outages, you're potentially going to run into those kind of issues. Structural mold failures, common failure mode for grinding or grinding mills, and that's something you don't often see sites have it as part of their maintenance PM to check. But I think generally most sites do have some kind of strategies to sort of check and monitor bolt elongations. And then trunnion bearing damage. Trunnion bearings generally are hard to sort of inspect, and we'll sort of cover it towards the end. And you have instrumentations and logics in place to sort of help you with that. Of course, during shutdown, it doesn't help to, it does help to do visual inspections if you can, as they can be easily accessible during shutdowns. And again, as I mentioned earlier, closing that loop in terms of the effectiveness of having those strategies. So again, having a review of your existing maintenance strategies, and obviously there's CMMSs, sites use CMMSs in which they can classify different failure modes and how frequent they sort of occur, and reviewing and addressing like what would those things that happen frequently, why are they happening frequently, and sort of going down the line of trying to address and closing that loop of maybe some failure modes are not included, or maybe trainings needed, things like that, just to close the loop and making those PMs more effective. And then equipment isolation plan, not optimized to allow simultaneous work. So again, it's a pain when you get to site and you can't really do a lot of work because of isolation systems. You can't work when other groups are working. So again, just it's sort of not part of maintenance, but it does play a role in terms of how you can manage a shutdown and be able to optimize the amount of work you can do within that shutdown. So I guess it's an important point to look at when planning those shutdowns is how we can better plan isolation, or at least so that we can allow more groups to work simultaneously and of course safely. All right, so just inventory management. Quickly going to go through quickly that. So again, for this slide, the key point here would be just spare parts, especially critical parts. They do need a maintenance strategy. So holding spares does not reduce the likelihood of failure. So that's pretty obvious, but it does reduce the consequences, right? So for example, logistically, it can be hard to get parts, especially with the really big lead time to remote sites. So it's really is worth the investment to sort of have a strategy in place to make sure that those critical spares especially are well kept. Correct spares of spare parts is critical to ensure a functional condition. So that's, again, it's unfortunately a very common problem that when you need the part at the time of the breakdown, it's never in the best serviceable condition, right? And now you have to sort of postpone work because you have to firstly get that part into the condition that you have to install it in. So it does add value, a lot of value, to make that first step. Having the right storage space for your critical parts, especially, and then of course cataloging those parts so that when you need it, they can be found easily and restocked when they're consumed. So spare parts storage, again, it seals in the point that of course, in terms of larger components like gears and mill bodies, it might be a luxury to sort of have them stored in a sort of roof or warehouse. But there has to be at least, it seals in the point that there has to be at least some inspection to ensure that, especially on those critical parts of the component, like the machine surfaces, especially for geared gear, for mill rotating elements, making sure there's those corrosion inhibitors are in good condition, and for large parts, it has to be, for example, geared gears, they have to be stored leveled. And that's because it can distort under its own weight if it's not leveled, and so that does become a big problem when you need the part and want to install it. So most parts that are supplied are packaged, at least for Metso. Most of those packaging is not designed to be stored long term on the outside or open weather, and so that's, again, seals in the point that spare parts has to be stored in a way that you can easily access it, and especially inspect those critical areas like the machine faces, and have access to making those inspections at least at a good frequency. So spare part maintenance. So the picture on the right is just an example of what we can typically see if it's stored out for long enough. Again, maintenance tactics are needed for spares. Critical parts, especially inspected to check for corrosion and condition of packaging. Typically, especially at least for Metso, we do have there's extended warranties that can be agreed upon when a part, when a component's such as a gear key, for example. So one yearly can go as far as 1.5, I believe, at the moment, where you could have a team come over and do an inspection for you, and just ensure that those critical parts of those big critical components are in good condition, or at least have some feedback on way to properly get them into good condition that can be usable when it's needed. And then obviously the last point there, components with assembled bearings should be rotated and sometimes lubricated regularly. So I think, again, for most people who are involved in this will know this. You have to, those examples are electric motors and gearboxes. You have to at least regularly rotate and just make sure that they don't seize while in storage. All right, so inventory part selection, when deciding parts or how much to, or which parts to stock, these are things to consider. So again, cost of, obviously, this cost of storing parts can be a costly exercise as well. So these just things to consider when making those decisions. So cost of purchasing, cost of storing and maintaining those spares, and I guess the consequence of not storing those parts. So again, it's a risk versus reward sort of situation where you have to apply a bit of, what are the consequences of not having those parts when we need it, or at least in the best condition at the time when we need it. So the image on your right there is just an example of how it can. It's typically, unfortunately, we like I said, we sort of see these a lot, and again, it's a luxury to have parts to be stored under a roof, but this is sort of what you can come across, where gear keys they're worth millions of dollars, and just investing upfront about just properly maintaining them can save you a lot more troubles down the line. Critical parts not inspected and found in unserviceable conditions when needed. Parts incorrectly cataloged, and so it's not able to be found when needed. Min-max levels, again, most that's a challenge of its own. You sort of determine consumption rates of different spares and try to find that good balance where you have between the amount you have to have before you trigger a reorder point or something like that. So commonly it's critical when it comes to for example, loop system components, right? So you got filters, seals, they high consumption in terms of because the equipment kind of goes through them because of the wear. And so those are critical because even though they're small parts of the system, they can shut down a whole mill if it's not I guess functioning well. Low value parts but critical. So again, they're low value, but they form part of that big system that if it's missing and if it's not available at the time when you need it, it can be a really big headache, just especially on production. And yeah, so some of the examples there, you got flow divider, accumulated bus discs. Just drop it in there. So this is it's just a case study that it happened on one of the sites where and the learnings from that is presented on this page here, where during an installation, because the site needed to save some cost, they didn't quite have enough or purchase the enough filters for that mill installation. And so it ended up being, it suffered from a contamination, and so they ended up going through all the filters that were supplied. So, going through, there's different ways that sort of people try to salvage and get the mill up and running, drying the filter or trying to clean it on the run and putting it back in using the same filter. And it's a small, you can sort of keep the mill running at that instance, but in the long run, if you damage, for example, if you have contaminants in your trunnion loop system, obviously ultimately can cause damage onto your journal surface in your trunnion. So this was just a sort of an example. Sustainable mill operation. So that's the other part apart from good maintenance practices. So again, sustainable mill operations is basically, so what it means basically is just to know your operating limits for the machine and stay within those operating limits. Know when to stop the machine. So again, that comes from at least understanding the consequences of, I guess, consequences of operating if in that condition, right? So if you do observe something that's kind of developing, and if you don't understand at least how long can it still operate. And again, it's understandable in the fact that most mining companies try to produce as much as they can, and so you can't sort of really shut down the mill every time for everything, but that just sort of gives point that you have to understand at least what you're looking at, and what would be the more severe consequences if we don't shut down the mill to attend to it immediately. And we'll go into that when we get into the examples. And then lastly, operating practices to avoid lock charge events. And I'll explain a little bit more as we go down. So knowing the machine operating limits. So what for any mill, it's designed to allow for there's a maximum ball charge limits that when they do the design, maximum charge levels, and takes into account the maximum mass or liner weight as well. So all this they agreed to at the start of when a process plan before it comes into it in operation. Those discussions are sort of made before that. So site and an OEM agrees on different numbers, and I guess the ore profile, how much they want to push through the mill, those sort of things. And so mills then designed, and there's it's important to know those information is readily available, and it's important to know the maximum ball charge, those limits are known, so that we maintain, or at least try our best to, as much as possible, operate within those limits. And those any modification to the body of the mill, or at least to any components, major components on the mill, does affect those limits. And so again, OEMs are there to sort of provide that guidance if in the event those limits have to be exceeded for whatever reason. Production mostly seem to be the case most of the time. Then ask, and there's always risk assessments that can be done to address those. Staying within those limits. So again, ball charge. So maximum ball charge, managing the ball charge level. This is something generally most sites leave it to methodologists to sort of maintain. So ball charge, for example, for power draw, mills are charged to maintain a certain level of power draw, and ball mills typically are very generally easy in terms of charging the mill to a certain power draw. And power draw essentially is is a reflection of good grinding efficiency. So typically there's a target of power draw in which they charge the mill up to so that they get the best amount of grinding efficiency. And there's an optimum point. You can't sort of overcharge your mill, then you run into risks of overloading the mill. And then SAG mills, typically they are more involved in terms of how they determine the right optimum charge level. So they consider things like the mill weight, liner mesh chains. So again, that's something that's determined normally after a reline. And then monitoring of those ball charge volume as a fraction of different power draw models. And again, methodologists typically manage this process of regularly doing charge surveys and determining that the best optimum level of charge to charge the mill with, and so to achieve the right amount of power draw and also grinding efficiency. So know when to stop your mill. So this is it's just an example. The picture on your right there is a loose flange bolt. It's between it's a joint between the trunnion and the head. So again, identifying faults early at the regular inspection is important. For most sites, they generally have a maintenance strategy in place to monitor those critical fasteners. And I guess the key point in this slide here is that to know when to stop, right? So these things can happen on the run. You could see, maybe slurry leaking through a flange, or even this where you could see loose bolts. And so just understanding the consequence of, if we allow slurry to sort of get into that interface or joint between the flange, most of the time mills don't. So it's almost like a death sentence for most mills when you have slurry getting into those interface. So it's sort of applying a little bit of science into the risk versus reward, right? So what are the consequences if we do allow it to run to the next sub, or we have to attend to it quickly, so get it addressed before it becomes a bigger issue than just a ball failure. Operating practices to avoid lock charges. So lock charges, for those of you who are not quite familiar with what lock charges are, again, the grinding mills, they contain slurry, and that's a mixture of basically rocks, clay, and so you can imagine if the mill, and this is an event that normally happens when you have a crash stop, right? So the mill for some reason trips out and you got slurry and ball charts sort of combined and still in the mill. And if that's allowed to stay long enough, you can imagine it becomes hard and can sort of stick to the wall. And so when you go for another startup, it can, the normal operation, you want those to cascade rather than just fall as it goes up during its normal operation, right? So that fall places so much stress on different parts of the mill, and it's generally it's basically not feasible to design a mill to sort of withstand the impact in which lock charge events can cause on those mills. So it's something that often happens, and it's one of those events that can happen, and it does not have to happen, a lot of times for it to cause a big issue. It can only happen once, and that's could be enough to set sort of like a chain reaction to those critical components like the bearings, or even your flanges. It could affect the integrity of those flanges. So operating practices to avoid lock charge events. So lock charge more likely happen due to greater fraction of fine ore than to ball charge volume. So again, like I said, crash stops normally, it happens during crash stops normally. And I guess with production being one of the things that pushes sites to or operators to get mills running, and that's completely understandable. But when you have crash stops and, if for some reason troubleshooting goes into like an hour or 30 minutes, depending on the type of ore that's in the mill, it can quickly turn into a lock charge, and that can be catastrophic. So again, during shutdowns, it's always advisable to grind out thoroughly so that you avoid those kind of events from happening. And then the last point there, ensuring interlocks can be in place. So again, lock charge is something that's it's hard to sort of measure, or it's an event that there's no instrumentation to measure that event, or you can only see the consequences probably later down the line. And so if it could be a good advisable thing where you have interlocks. So if the mill shuts down for whatever reason during a crash stop, and if it goes beyond, let's say, 30 minutes, it's advisable to probably inch the mill a few revolutions, or just to free up those charge before you can go for a run. Okay, so catastrophic failure modes. So this is sort of like the part where we go through some examples of different failures. And we'll be mostly focusing on these critical, I guess, events or parts of the mill. So you got ring gear tooth fracture, mill body wash erosion, and then lock charge event, which is what we just briefly gone through, and then trunnion bearing failures. So gearing. Geared gears, they again, there's different failure modes. There's different ways in which a geared gear can fail, and the severe ones can be overloading. Again, overloading can come from just overloading your mill with charge. Severe misalignment that could easily be from installation, or even overloading your mill could change the alignment. And then severe surface effects or severe wear that can ultimately cause the crack or fracture of the gear teeth. So the next slides, we'll just go through some mitigation tactics. So mitigation tactics or at least mitigation strategies to at least hopefully address those different failure modes. Lubrication being a really important part of ensuring that those are managed. So we've seen examples or scenarios where for some reason the lubrication system did not kick in, and then a new gear was scuffed within an hour of operation. So that can happen. An hour is actually longer, but you can easily scuff a mill because at startup it's really high load. So you try to overcome the inertia, and it can easily scuff within less than an hour. You can scuff the gear and badly damage it. And ensuring adequate instrumentation, again, air pressure, lubrication delivery. There's definitely has to be different maintenance strategies in place to sort of inspect those systems during shutdowns. And interlocks are there to most for good reasons, and that's to not only safeguard the mill, but it's for safety reasons as well. So it's really highly advisable to sort of not bypass those interlocks unless you properly understand the risks and consequences of doing that. Spray pattern check is generally something that's quick and easy to do. It can be done, in a shutdown. It is it's very effective in terms of showing you at least a good coverage of lubricant gets onto the gear, and that way you avoid, at least you have confidence that your lubrication system is somewhat working as it should. Built-in IR systems, that's something that's available. Sites condition monitoring is generally managed, and they do periodic maintenance to check temperatures on the pinion bearings and the drivetrain. IR systems, you can sort of have sensors which and trigger alarm points to help you, I guess, be more have a trend and have some more tracking on those on your pinion temperatures, and that can trigger if there's an event or if there's something wrong with the lubrication or issues with the alignment. Normally, temperature is one of the main indicators that something's wrong with your gear. This is just I'll just put it in there. It's IR sensors. Again, IR sensors have come a long way from just displays of numbers to now they can produce thermal images like this one. So it is good in terms of giving you a good visual of the temperature profile across the pinion. So this is just one of the key mitigation techniques. It's a nice to have, sort of, so you can, even if you do have failures in the gear system, you can always have a trend in which you can go back to sort of see different parameters, and temperatures being one of them, to help you with the troubleshooting process. So this is the ring. So part of the key mitigation tactics, this is an example of a gear loop schematic. It's I guess an example of a good, well-designed gear loop schematic for a gear. And I guess I wanted to point out is what this highlighted in yellow in here. So you got the air pressure switch to monitor the pressure at the delivery point. And then there's a proxy that counts the cycles, the number of cycles for the loop. So this is normally a cabinet that's directly closer to the delivery point of those of the lubricant. So at least you have those needs to be monitored, and it's something to be aware of if you do have a system, and just so you can be understand at least your cycles are working as they should. So they're cycling through the delivery pressure in terms of the air to I guess cause the lubricant to spray in good pressure. So this is an example of why we have to monitor pinion temperatures. So again, acceptable alignment profile on a pinion. So you got the pinion gear meshes with the gear. This begs the question of, and normally alignment issues do come up, and so sometimes it's basically due to just different in operating limits. So you probably add more weight. Overcharging your mill could change the alignment slightly, and that could all of a sudden sort of cause the temperature profile to change, or it could because of an event where you got a slurry ingression or something like that causes one part of the gear to wear out more than the other, and so it changes the temperature profile. Basically, what we sort of advise to most customers is the point at which you can sort of have to stop and really try to plan adjustment for your adjustment so you can get the right alignment is when it goes beyond at least 8 degrees. And again, a temperature change in the profile does not always mean that it's to do with alignment. It could be a lubrication issue. So you got nozzles probably clogged up. You need to probably clear. It's not delivering the right amount of lubricant onto the gear, and so you got less delivery on one side, and then so it hits up, and then it gives you a false sense of indication that it's something to do with alignment, whereas it's probably to do with lubrication. So once you've verified those, then you can sort of go through this part of, okay, that might be alignment issue. So you can sort of try and look at ways in which to adjust the pinion so that you get the correct alignment. Gear mitigation tactics, this regular crack detection through NDT. So this is a fairly common practice in the industry. NDT using either eddy current array or the traditional MPI. MPI is I guess the only difference there is MPIs can be, it's effective, but it can be slower in terms of how it's conducted because you have to clean the surface. But eddy current array seems to it's faster, and it can sort of do it within I guess Metso does offer a service in which eddy current is deployed. There's other competitors who do the same, but it's sort of like the new and I think the best sort of way to inspect gears at this point. Again, it's important, and that's another point I probably wanted to bring up for gear inspections. A visual inspection does go a long way. So things don't come up as crack until later down the line. So it normally appears on the surface and then sort of develops into that crack. And so the visual inspection does go a long way. So for example, if you have a out of round gear, for example, you might have only pithing on one section of the gear, and the rest of the section might be in good condition, because that particular spot comes into, I guess, more contact as it rolls around. And so a visual, ideally 100% if it's possible, that mitigates those kind of issues where if you do have conditions where the gear is not out of round for an event like, for example, lock charge, could cause distortion of those critical mill components, and then all of a sudden you probably see a temperature variation on your pinion alignment, and then it's something that you probably won't even explain unless you have regular inspections and ideally 100% of the gear. So yep, one of the ways to sort of mitigate is again stressing on the point of spare parts, especially critical spares. They need a strategy, and in this case, for ring gears, most of the sites have been operational for a long time, and so what you probably have in store, I guess it's good knowledge to know that they're compatible. So what you have in store has to be compatible with the old or the running mill that you're intending to install it. So what it means to be compatible would be just looking at the flange connection designs, even with the indexing on the holes of the way in which the gear is bolted onto the shell. So it's probably something that seems to be very straightforward, but that's something obviously something that needs to be considered if you're obtaining a spare and going down this decision of keeping a spare on site. That's just one of those due diligences that has to be done prior to obtaining a spare. Yep, so you got store gear properly, so inside well supported, only because those gears, as I said, if they're not well supported over time, they can distort under their own weight. And then yes, having regular storage inspections. So again, those gears, they have machine surfaces that and then they generally are coated with corrosion inhibitors. And those inspections can just be about just inspecting those specific points. And when storing those gears, I guess, has to be stored in a way that they can be easily inspected in storage. So this is a quick reminder of what could go wrong if gears are I guess if what could go wrong if things just happen. This is a severe case, but of course this is just a quick reminder of what could go wrong on the gear. So mill body. Mill body, I'll just quickly run through this ones because I think I'll hit 1 o'clock on the dot. So mill body wash, again, it's a common failure mode. Most sites probably, in my experience, at least they react to this most of the time. So if they observe during a liner replacement that those rubber backings are not in place, or if they have come off, then they sort of patch it and let it run for the next shot. And that's kind of like most of the time, that's all it takes to sort of progress to that stage where you can risk damaging your trunnions. In this picture here, you can see this is the interface joint between the trunnion, the trunnion and the trunnion liner. So that's on the inside. After you've removed the liners, there's a rubber backing, and that rubber backing normally is those joints. They're sealed up with Sikaflex just to prevent any kind of leakage into those joints. In this case, this is an example of one of the customer sites. This joint is supposed to be, about half a mil, and just for reference, the whole thumb could probably fit in there in this part. So it definitely, it was something that it was noticed previous shots before, but they sort of patched it up. Slurry sort of leaked into that interface, and it got, worst case scenario, it gets into the void between your trunnion liner and your trunnion, and that can be very catastrophic because it races as the mill rotates. And so, yeah, these points, obviously, it's hard to inspect only when you get to see those points to inspect during a shutdown. But it is important because obviously the consequences down the line if it's left uninspected are more severe. So this slide here just basically points out just different critical points in which, of course, they are hard to inspect and generally they become a really big issue because of their location. They're so hard to inspect, and so when you have slurry getting into those joints, then normally it becomes catastrophic. So you got, your mill joint here, that transition interface between the head and the trunnion. These joints, they're hard to inspect when it's running, but you can, if you have a maintenance sort of tactic, at least to align with shutdowns, to be intentional with, at least inspecting those points, because it can catch and it can be very costly at the end if they're left uninspected. In terms of the stress, these areas are high in stress concentration. So anything, I guess, in terms of the stress profile, it's higher in this end, and it sort of reduces as you come in between. And that's because the support of the bearings are right here. So these are high stress areas. And so if you could imagine if there's erosion in these areas, especially those joints, and as the material wears out, it becomes very susceptible to fracture. And that's basically that's the end of a mill. This is an example of a wash. Again, this is a joint, an example of the joint here. So you got the liners, they sit here. The rubber line backing is somewhere here, and this is the joint. So this here is basically here. In this example, this is between the head and the trunnion. So racing was left unchecked, and this is those holes are basically bolt holes. So they basically worn through the trunnion, and in this instance, it's hard to do much to salvage. It's a mill replacement when it gets to that point. And this is a good example of what could be a severe incident if it does left unchecked. So again, inspect the inside the mill behind the liners, every reline, especially on those joints, and specifically check at those flange interfaces. That's very important, and the condition of the rubber backing inside the mill. It would be good to have at least some kind of strategy in place to, or at least some allowance during shutdowns to properly rubber line if it's found during a reline that those rubber backings are peeling off. So broken flange bolts, they are always a serious problem. So they, again, flange bolts, when we talk about flange bolts here, these are those critical flange bolts. So in these areas, these are, in terms of stress locations, they experience the highest stress during operation normally. But when you have, for example, lock charge events, it could place so much stress on those regions that you could have, for example, a flange bolt breaking because of those extreme force stress that it's been placed under. So flange bolts breaking is a symptom of the racing that could be happening within the flange. So again, it brings about the point of understanding the risks. If you don't attend to a flange bolt breaking, what are the consequences if we don't shut the mill immediately to plan something to attend to? Investigating broken flange bolts is an immediate action, so that's something that's highly recommended. Again, as I mentioned earlier, once slurry gets into those joints or those interface, over time it can, for some there's rarely some cases the joint can stabilize, but most of the time if it's left unchecked, it won't. And if you have a bolt that's broken on a flange, ideally, you should obviously shut the mill down and then you check tensions on bolts that are in the area or in the region, because normally what happens is the bolt that's broken has sort of transferred its load to the neighboring bolts, and you'll find most of the time those neighboring bolts they're being stretched because of those added stress. Flange bolts should have regular inspections. So again, the common tactic here is bolt elongation checks. So this is something I think most sites they do regular bolt elongation checks. It could be 3 months to 6 months, just to check, making sure that those elongations are within specs, and and that's all you have to sort of invest in to ensure that those flanges are intact. So mill body wash, one of the mitigation tactics that sort of Metso you can sort of employ is ultrasonics. Right? Metso has sort of developed a sort of rapid scan technology. It basically employs ultrasonics to map out wash regions on the mill body. It's easier and faster in this case, so you can sort of easily accessible from the outside, and it doesn't have to be on a reline where you have to go into the mill to have the liners removed to inspect the surface, or even the rubber backing removed to inspect the surface. But you can easily do this during a shutdown if it's not a reline, but if you suspect wash that you have to track, that can be done from outside. So it's just a technique that's Metso sort of developed as rapid scan to map wash. Again, this is a reminder of consequences of not managing a body wash. So this one, this mill collapsed. So this is the cradle under the mill. So you can see, so mill collapsed onto the foundation. So that's mostly because the trunnion is worn out and basically collapsed, fractured. Lock charge events. So we've sort of touched on lock charge events early on, but this is the consequences of lock charge events, and I've sort of mentioned it along the presentation, so I'll quickly just run through it. So again, obviously, to avoid lock charge events, because the consequences of lock charge events can be really severe. Again, it can damage your bearings, trunnion bearings. That load gets transferred all the way down to, apart from your flanges here, to the bearings and the drivetrain as well. So damage to mill flanges can cause flange prying and then slurry when it gets into those interfaces. It's the only way to sort of mitigate that. You can sort of replace bolts, but if you do have slurry still in that interface, and if it's a lock charge event and you have distortion on those flange, it's really hard to even stabilize the flange from that point on. But if there's racing inside that interface, your probably best bet, cheaper option would be machining that face, and that requires obviously an extensive amount of shutdown to basically disassemble that flange, then machine it in situ. Replacing a mill, it's essentially replacing a mill, but at I guess a lower scale. But yeah, it's really hard to come back from that when you get slurry in this interface. Again, pictures really seal the importance of lock charge, why it's important to just make sure that if it takes a few minutes to inch the mill before starting up, it does pay in the long run. So critical inspections could be visual weekly, just walking around the mill, just looking at flanges, looking for leaks, and most of the time, if the flange integrity is affected, you'll quickly see slurry seeping to those flange. Ultrasonic inspection is one of the ways to sort of, as we touched on earlier, monitor or even check for relaxed bolts or even cracked bolts. Again, yeah, last point, yeah, if slurry enters the joint, it's the bolts going to suffer from fatigue failure. All right, so the last failure mode there is trunnion bearing failure. Again, trunnion bearing failure can be caused by there's different ways in which it can fail, and we've sort of touched on a little bit of those through the presentation. So lock charge event being one of them, lubrication system failure, and then severe oil contamination. So misalignment or even motor tripping. So lubrication failure, even in the lubrication system itself, there's components that are small, like for example, seals. They high consumptions, but if you can have an effective strategy that maintains inspection of those shields and proper inspection as well, that goes a long way in terms of protecting the trunnion, because you could have trunnion, you could replace your trunnion bearing if it suffers from, let's say, abrasion. But if that becomes severe to the point that it starts affecting the trunnion journal, then that's something that's going to really kill the mill. So in this picture here, it's basically they're trying to machine in situ a trunnion journal and replace the bearing. So key mitigation tactics for pad and sleeve bearings. So and control logics. These are parts which during operation they can be monitored. The conditions or these can be monitored using existing control logics and PLCs in place. Set points, typically when equipments are installed, they come with preloaded set points to sort of have triggers to have inspections or even during operation. So if all your parameters are in good, then the set points are just there to sort of give you a heads up of when to attend, or at least draw your attention to an issue that might be imminent. So maintain lubrication, loop system, trunnion seals, as I mentioned. Trunnion seals, if they wear out, it's a high wear component, but it's the replacement does not probably cost as much, but the consequence can be a lot in terms of on the mill body. Again, lift checks are recommended if during shuts, they're very easy to do. Lift checks just to and normally you have low limits or alarm limits on your PLC, and that's sort of worked out from those lift checks. But it's an estimation, so it's always good to have lift checks done, just to ensure that you have enough lift so that it prevents at least the risks of abrasion or wearing out your bearing. Again, visual inspections on those journals or bearing journals during shutdowns it's quick and it's easy to do. So yeah, that's something that needs to be considered. Spherical roller bearings, normally for smaller sized mills. Again, maintenance strategy in terms of monitoring the condition for those spherical roller bearings. Vibrations can work, but because of the way in which they're really slow, and so it might not be as effective. In this case, obviously, spherical roller bearings, greasing lubrication system has to be at least optimum, and bearing temperature seems to be the best trigger for at least trigger to sort of plan not only change up, but to investigate, what a problem that might be developing on those bearings. Although vibration analysis can at least still pick up bearing defects early on. Quick reminder again on consequences of failures. This is a trunnion. On the left, you see it's probably not going to be easy to salvage this trunnion. On the right, it's a journal, or it's one of the spherical roller mounted mills, and so the journal's been machined because the inner race of the bearing rotated, and so it caused wear on the journal, and so they have to remachine the trunnion and obviously change the adapter sleeve to replace the bearing. That's just one of the examples. So that's I guess that's the end of the presentation. In terms of like questions that we might have, I'm not sure if I didn't check the questions, but if there's any questions, just feel free to sort of reach out if you do have questions. If I don't have the answers, we have a team who's experienced in a lot of aspects, from grinding to pretty much everything. And so, I can always direct your queries if I don't have the answers for them. But yeah, this is my email. Just reach out if you do have questions, specific questions on grinding mills or anything. Thanks.
Thanks so much, Jesse, for your time. Yeah, we can leave the floor open for 3 to 5 minutes if anyone has any questions. And yeah, if Jesse's able to answer them now, we can definitely have that. So the floor's open for the next 5 minutes. I see Isaac as a question there. Jesse.
Yep.
And that's 4 questions. Isaac at the top first, and then Elizabeth at the bottom.
Okay. So liner management. Oh, okay. So liner suppliers. So there's it's so typically when I guess when they install a mill, it's different vendors sort of have that offering to offer liners. It can come down to the fact of what you sort of experiencing on site. So if you may be experiencing a lot of wash, depending on the failure mode, right? So if your liners are wearing out consistently, even before the time you have at the moment in terms of your inspection frequency to inspect before they wear out, then it's something to consider. It might be to do with the material of the liner, or it might be processing where you just feeding, obviously overcharging or operating the mill outside of its design limits. So yes, that's a consideration that you can sort of consider having suppliers to, if you have a problem, you obviously have to go to them and say, hey, look, we're experiencing liner cracking, or even though we're operating within design limits, we're still having liners washing through before the change out dates, and it seems to be working before, but then all of a sudden it's now different. So there's there's this option of obviously you have to consider those before going to an OEM or someone who provides those services to and ultimately it's up to the company, right? So they can choose if they want to have you know, more than one vendors. Ideally, you want to have, you know, one vendor or supplier of liners if you trust and have that working relationship with them. And that's good in terms of providing technical support for a particular site. They sort of have an understanding of the history, and so when they provide support with regards to liner, they can be specific, and they're and even with improving, you know, if you have failures as such, they can, because they have already, you know, history and data on the mills, they can provide feedback or actions to look at which are more effective, right? So they, because they have history. But obviously you want to keep it to one, but that's something that's up to site to decide based on, you know, if they're not seeing the value, then they can, it's up to them to sort of, hey, look, we need, it's in the business interest to sort of explore other suppliers who might solve a problem that we have. Okay. So measuring charge level, power draw is just it's an output. It's a good measure of grinding efficiency, right? And so what you will see sometimes, and most mats, it's probably not my best area expertise, but most mats, what they do normally is they jump into the mill to physically measure the ball charge, right? And they do this by pulling tape measure literally and try to measure the volume, right? So you could have mills that are designed to up to, let's say, 35% ball charge, and that can increase when I guess sites, when they would, let's say, for example, want to push production, and so obviously you've got more ore coming in, and so in terms of charge volume, now you've sort of increased charge volume. Again, it has to be an optimum level, but power draw is generally the good measure of optimally charging your mill. So you reach that power draw where, and sites, because of experience, the output of the mill, for example, the sizing of the discharge, it comes into play of okay, this is the, I guess the right amount to charge, you know, whether it be 35 or 40% sometimes, charging just to get that grinding efficiency. But that's probably the best way, I would say. Yeah, so crash stop, again, crash stops, they can happen for whatever reason. The mill can trip. You could have a procedure in place. Like I said, a procedure can be in place, but if it's just written on paper, then it, you know, because operators tend to do that a lot, where they just, because they want to get production going, you know, if it's something on paper, sometimes it's easily can be overlooked. And so it's my advice, you know, it's suggested, but it's something that you can sort of incorporate into the interlock. So, for example, if the mill goes into a trip, and then an interlock would be, okay, from the time it trips to, let's say, 30 minutes, an hour, if the mill doesn't come back online or starts back up for whatever reason, maybe troubleshooting, then an interlock would kick in where you have to inch the mill so that you free that charge up before you go for a startup, right? That's just a suggestion. But however way the site need, you know, the logistics of how they can do it, it's up to them. but that would be good in terms. So if it's in the interlock, then they have to sort of meet that condition before the mill goes into a startup. So it's just that would be a good sort of thing to have in your interlock system. I hope that answers question 2, Elizabeth. So yeah, I gave an example of 30 minutes, right? But depending on the ore and if it's fine material, clay, it tends to harden up pretty quickly. So, you know, like I said, the consequence of having a lock charge event is so much, it so much outweighs, just maybe an hour to inching the mill or connecting the inching drive and inching the mill. What's the minimum? I take it that your question 3 is the minimum clearance between, or the gap between the bearing and the journal. Is that what your question is? Okay, so Ray, for your question, normally spherical roller bearings, they can take in axial thrust. Roller bearings, just strictly roller bearings, they can only take radial loads. So that's why for smaller mills, the radial thrust is accounted for by the spherical roller because they can take in radial loads as well as thrust loads. So it's accounted for. Common failure modes, generally most mills, it doesn't really, of course, spherical roller bearing mounted or sleeve bearing mounted mills. The general failure modes, as we've covered, are the same, generally the same. They experience similar kind of failure modes. So, looking at your lubrication system being one of the most important ones, seals, drivetrain, condition monitoring, employing condition monitoring, especially if you got vibration analysis on site, to just making sure that, and baseline data is collected so you can have something to compare to. And so when failures, or at least when failures developing, you sort of have a starting point to trigger your actions. But yeah, it doesn't really matter if it's spherical roller bearing mounted or sleeve bearing mounted. Most of the common failure modes we sort of touched. Of course, the loads is slightly different, but yeah, that's something that's fairly common across. Any more questions?
I guess that's all the time we have for questions. Thank you so much, Jesse, for your presentation. Really excellent presentation. Definitely a lot to take away for the audience members. So yeah, thank you so much. On behalf of the IEPNG POM branch, the executives, on behalf of myself and my team, we thank you for taking the time to prepare your presentation, have it vetted through your managers and supervisors to just have it in ready for today and to have this presentation. So thank you so much for your time. For everyone else that are still here, we're going to have more technical talks in the coming future. So stand by for that. Just stay tuned to our LinkedIn pages, Instagram, all the socials. and we'll keep you posted. But on behalf of myself, you guys have a great rest of your day. Yeah, thank you again, Jesse. Thanks, guys.
Okay, thanks. No worries. Thanks for having me, guys. Yeah, you guys have a good day.
Thanks, Jesse.
Cheers. Thanks, Jesse. Thanks, Murphy. Bye.
Thanks.
Hey, Oswald, thank you. Isaac, thanks, Isaac, for joining. Victor,